All right, so the next section in calculus deals a lot with optimization. In this video is to present the broad strokes and processes that we'll be using to find these. Now to start, we're going to talk about the max and min, and this goes for relative or for local. And the maximum and minimum we often use to find a function. Say we want to look at volume, right? Volume is cubed, but the derivative is a parabola. And we want to say, okay, when is that going to be maximized? And there's a great way that we have of doing that. If we take the minimum and maximum points here, and we draw our tangent line, or the derivative at that point, what we get is a horizontal line. Or when the first derivative of our function equals 0, that is when we have our relative or local max and mins. And so we're going to go through a process of setting the first derivative equal to 0 and testing points to see when it's a maximum and see when it's a minimum. Now, if we look here at this first point, first our slope, our derivative, is going to be increasing, right? And then it's going to be decreasing. And so when we have a max, we have our derivative is first increasing and then decreasing. Or we have a positive slope, then a negative slope with that derivative, and that's a max there. Now we have a minimum on this side. We have a minimum when the slope or the derivative is first negative, or it's going down, and then it starts to go positive. And looking at the first derivative, which is the slope, and seeing if it's positive or negative, it helps us to determine if it's a minimum or a maximum. So the next point that we're going to be talking about is concavity. And we have times where it's concave down, or it's kind of like a downward parabola or an upside down bowl. So that's concave down. And then we'll have times when it's concave up or upward. Now concavity we find with the second derivative. When we set that second derivative equal to 0, we get what are called points of inflection. And what happens is we have a point where the slope starts one direction, it kind of stays constant, and then it switches the other direction. And this is called our point of inflection. Inflection. And so if we look here, if we have some concave down right here, and then it will start to switch to become concave up. And then it comes to a point where that changes. It becomes concave down again, and then concave up. So concavity is where the graph starts to go and switch a little bit. And we find this by setting the second derivative equal to 0. So we've kind of talked a little bit about what it means for a maximum or a minimum or concavity. And there's a process that we go through to find this for each thing. The first thing that we do is we derive, right? And then we find the critical points or the points of inflection. I'm going to say CP for critical points or POI for points of inflection. Then we set up a number line. And we test points along that number line. And really when we are testing for points, we really are looking at, okay, are they positive or negative? So a factor could be, a point that we choose on the number line could be positive or it could be negative. So this is a practice to show what we're going to do. We're going to have a number line. We've taken our function and we've derived it, and we've gotten that our derivative, it's all nicely factored out. We've got x plus 10, x minus 10, x plus 2, x minus 2, right? And whether or not it's the first or second derivative, right now we're just looking at the process. So luckily we didn't have to do this. We map our critical points or our points of inflection. So we have 0, positive 10, negative 10, negative 2, and positive 2. So we'll put these on negative 10, negative 2, 0, 2, 10. Then what we do is we look and we pick a point. So right now we're going to pick a point over in this section over here. And oftentimes just choose a point that's easy. And so I'm going to say, okay, I'm going to choose negative 20. And I'm going to put that in for each thing. So here, x is going to be negative, and negative 20 minus 10 is a negative number. Negative 20 minus 10 is still a negative number. And negative 20 plus 2, well, that's still negative. Negative 20 minus 2, that's going to be negative still. So then I count up my sign changes. It would go, because everything's being multiplied together, remember. Negative times negative is a positive. So positive to negative is negative. Negative to negative is positive. Positive to negative, okay, that means that the overall slope or the overall derivative here is negative. And so next I'm going to choose, let's try this next section here. Let's say negative 5. Alright, so negative 5 for that. Negative 5 minus negative 10, that's going to be negative as well. Negative 5 minus or plus 10, that's going to be positive. Negative 5 plus 2, that's going to be negative. Negative 5 minus 2, that's negative 7. So I'm going to be negative times a negative is a positive. Positive times a positive is a positive. Positive times a negative is negative. Negative times a negative is positive. So overall, in this area, in this interval, my function is overall positive. And that means that however the graph looks, it starts by going down and then starts to go back up, which means at negative 10, I have a relative or a local minimum. And then we would continue the process with each section. For time's sake, we'll do just one more. So let's take here. We'll choose negative 1. And if we follow the pattern that we've got here, negative 1 and negative minus a negative 1 is still going to be positive. This is negative. Negative 1 plus 10 is going to be positive. Negative 1 plus 2 is going to be positive. And negative 1 minus 2 is going to be negative again. So negative times a negative is going to be positive. Positive times a positive is positive. Positive times a positive is positive again. Positive times a negative. That means that our overall function for this interval is negative, which means that whatever that derivative is, however steep it is, it's going back down. And we've also found another maximum, or a maximum here. Now sometimes you'll get where it's positive and positive and positive on all three intervals. It's not always going to switch. Alright, so we're going to do a quick walkthrough of a simple problem. We're going to take our function is x cubed over 3 minus 16x. The first thing that we do is we take the derivative. We use the power rule, we bring that down, And the 3's cancel out, so that means that our f prime, or our first derivative, is x squared minus 16. And luckily this factors nice and easy. So we've got x plus 4 and x minus 4. We take and we set that first derivative equal to 0, and we solve. So we get that our critical points are 4 and negative 4. So we're going to set up our number line for negative 4 and then positive 4. And we're going to do tests along this line to see what happens. Now remember that our derivative is x plus 4 times x minus 4. Sometimes it's easier to leave it in factored form, and so that's what we're going to look at today. We're going to pick a number for this first interval, and we're going to say negative 5. So if we put negative 5 plus 4 times negative 5 minus 4, this first number is going to be negative. The second number is going to be negative. That means that for this interval, our derivative is positive. Now let's look at our second interval. Let's pick a nice easy number here. Let's do 0. We've got 0 plus 4, 0 minus 4. That means that we have a positive and a negative multiplied together, resulting in a negative over here, and a negative derivative or negative slope. This third section, let's choose 10. Doesn't really matter what you choose as long as it's easy. 10 plus 4 gives us a positive number. 10 minus 4 gives us a positive number. So overall, this section is positive, which means that our derivatives are going up, then back down, then up again, which means that if we look at this point 4 here, negative 4 is a max. And if we look at 4 here, we've got down and then back up, which means that 4, positive 4, is a minimum. Now we're going to do a quick walkthrough of a second derivative test. If we remember from our last example, we got that our first derivative, our f prime of x, was x squared minus 16. We then take the derivative once more for an f double prime of x to be 2x. And our next step is to set that equal to 0. All right, 2x equals 0. Luckily, that means that we get, if we divide each side by 2, we get that x equals 0, which gives us 1 point to test. So we set up our number line, 0. We can choose a negative number on this side. So let's choose negative 10. And on the other side, we can choose a positive number. Let's choose 20. So we'll put this in for our x and our second derivative. And it's 2 times negative 10, which gives us a negative number. And then over here, if we put 2 times 20, because we're putting 20 in for our x and our second derivative, we get that our second derivative is positive, meaning that our critical point is at 0 is our point of inflection is at 0, meaning at 0 it starts to go from being concave down to concave up. I hope this was helpful. We'll have more videos going into more detail, but just remember that the process is that we find the derivative, whether they're first or second, we set it equal to 0, and then we test points to see if the slope or that derivative is going to be positive or negative. Have a great day.